Hi everyone, my name is Amitesh, and in this video we're going to prove the most important theorem in differential calculus arguably, which is Rolle's theorem. And I've written the statement down here. We're going to unpack it, we're going to go through it in detail and explain the thinking process of a mathematician of how to go about proving a theorem like this, how to intuitively get an idea and then make it into a mathematical proof. And even if you have no introduction or previous experience with mathematical proofs, this video is for you. Okay, so let's just dive right into it. I've taught this multiple times at Princeton University in freshman calculus, and I'm going to present a proof which I really love and how we kind of think about it. Okay, this is the standard proof for Rolle's theorem. So how does this work? So the argument is going to be the following. First of all, what is the theorem telling us? Okay, that's the first step. The theorem is telling us, in some sense, it's kind of a discussion around the idea that what goes up must come down. Okay, so what do we mean by this? We have a function and we know that on some interval a, b, we know that it has equal values at a and b. Okay, so it has some value at a and it has some value at b. And we're going to connect and say that you're going to have a graph that is going to go from a to b continuously. Okay, so it's a continuous function. You can draw the graph with one stroke of the pen. Okay, so whatever draw, you sort of draw some squiggle, whatever you like. You can draw something like this. This is an example of such a function. And we're requiring it to be differentiable. Okay, so here we say continuous on AB, which means it doesn't have any breaks anywhere in the graph, and differentiable on interval AB. So when I first saw this, this confused me. Why do we have the closed interval here and the open interval here? Why do we include the endpoints? So continuity at the endpoints is going to be important, otherwise the theorem is false. Differentiability at the endpoints doesn't really matter. Okay, so we just kind of care about differentiation or differentiating the function inside the interval. And then what we're saying is f prime of c is going to be 0 for some c inside the interval. So what that means is that the derivative is the slope of the tangent line. So that means we're saying that at some point in the interval there is a horizontal tangent line. Now once you've grasped this, once you've kind of grasped the statement of Rolle's theorem, you kind of see that it sort of feels obvious in the sense that if you have a continuous graph from a to b, it has to kind of at some point, if it goes up, it has to come down, right? What goes up must come down, and then kind of the apex of the graph is going to be where the horizontal tangent line is going to be. On the other hand, if it goes down, it must come up. So this is actually a very good positive thinking for life as well. If you go down, you must come up. And it's the same kind of idea here, that if you kind of write down this graph, again, it's the same principle. If you have the graph, if you go down, you have to come up. You could come up multiple times, but Rolle's theorem only says that at least once, you're going to have a horizontal tangent line, but you could have many horizontal tangent lines. So that's what the theorem is unpacking. Okay, so that's what the theorem is unpacking. It's Rolle's theorem. Now, how are we going to prove this theorem? Okay, so proof means it has to be a watertight argument. We can't just draw some graphs. Someone might say, like I can draw a graph that doesn't look like any of the ones you've drawn. Yes, it looks like it's true, but how do I know there isn't some weird graph where this is false, right? How do I make this an argument, a watertight argument, as solid as any other proof we've seen in math so far? Studying differential calculus, what is the limit definition of the derivative for the power rule or for sine x or whatever it is? How do you make this watertight? So this is actually a very interesting exercise. I want you to think about how you'd make it watertight, and I'll present to you how I look at it as a mathematician. So the way I think about it is that, and drop me a comment down below, how would you explain this to someone? How would you explain Rolle's theorem to someone? Do you have any interesting perspectives on it? I'd love to hear your comments down below. So the way I kind of look at it is that we want to target what our intuition is, we want to target that. Okay, so our intuition is that when it goes up, it must come down. What is the point where it has a horizontal tangent line? It's going to be at a peak or a dip. And these are what we call in calculus a local max or a local min. Okay, so local because, for example, in this picture, here you have a peak, here you also have a peak. This peak is smaller than this one, but this is locally a max in the sense that nearby all the values of the function are less than this apex. Okay, so this is what we call local max. And what we kind of want to say is that, okay, if we can find a maximum of the function or a minimum of the function somewhere on the interval, then that is the point we want to target as having a horizontal tangent line. So then we have to mathematically prove using the definition of the derivative why the tangent line will be horizontal, why the derivative will be 0. Okay, so let's kind of get into that. Okay, so let's kind of write out the argument. So we kind of identified our strategy is to argue that there has to be some extremal point, max or a min, either a deep or a peak, okay? Why is that? So we're going to have to invoke a theorem that unfortunately I'm not going to prove in this video, but I'll do another video on it. It's the extreme value theorem. It's called EVT, okay? Extreme value theorem. What does the extreme value theorem tell us? It tells us that a continuous function on a closed interval has a maximum and a minimum. Okay, so this is the statement of the theorem, that a continuous function, and watch till the end for me to discuss as well why if we omit any hypotheses here the theorem fails. Okay, but I'm just going to recall the extreme value theorem. A continuous function on a closed interval AB has a max and a min. Okay, has a max and a min. Okay, so these are global max and global min. Okay, the absolute maximum point and absolute minimum point. They could be equal if the function is constant. Okay, so then in that case, Rolle's theorem is saying the derivative is 0 everywhere, for example. But why? Okay, once we've accepted this theorem, which is a separate important fundamental theorem about continuous functions, how are we then going to exploit it? We're then going to prove the derivative is 0 at the max. Okay, and this is a really fun exercise. I really love it. We're going to use the definition of a derivative. Whenever you have a proof, you have to go straight to the definition. Okay, so the proof is going to be the following. So here's the proof of Rolle's theorem. So this is the extreme value theorem. I've written Rolle's theorem here, so I'm now going to prove it. I'm going to erase this from the board. So we are going to take a max or a min, and we're going to look at the limit definition of a derivative and prove that the derivative is 0. Okay, and we're going to think about this very precisely. Let's prove it for a max, and I want you to think of what the argument is going to be for a min. Write it out as a proof, as an exercise to really master mathematical proofs. Write it out as a proof, or explain it to your friends or family. That's the best way to really grasp things, I feel. Explain it to someone. You kind of really have to think about it then in a different way. So suppose you take a max. So let's take a max. I'm going to show that the limit definition of the derivative shows the derivative is 0 at a max. It's also true for a min. So that's what I'm saying, I encourage you to try to prove. But let's sort of say you have a max. So I'm going to draw the picture here. You have a max of the function. Now, how are we going to show the derivative is 0? Okay, so this is a fundamental calculus fact that is useful even beyond Rolle's theorem. It is why we study critical points, to find extrema in optimization. So here's the proof of Rolle's theorem. So the proof is going to be the following. What we're going to do is we're going to say that by the extreme value theorem, okay, the extreme value theorem, which I'm going to abbreviate as EVT, the extreme value theorem implies that f has a maximum. Implies that f has a maximum or a minimum. Okay, a maximum and a minimum. Okay, now the next thing is that f may not have, the maximum we want to be in the interval, open interval AB. We want it to be inside the interval because, if you take something like this graph, for example, this hypothesis of Rolle's theorem is satisfied, but you don't have a minimum. You only have a maximum. Your minimum is at your endpoints, but the derivative is not really 0 there. Okay, so you don't have the horizontal tangent line there. So what we want to do is we say, okay, f has a maximum or minimum. We know that if f is non-constant, if f is constant, the theorem is obvious. Okay, the derivative of f is 0 everywhere. Okay, so we assume without loss of generality. So I say assume without loss of generality that f is non-constant. Okay, so assume without loss of generality that f is not constant, and also not just that f is not constant, and also that f has a maximum that is bigger than f of a and f of b. Okay, and f has a max at x equals c inside the interval AB. Okay, so assume that f has a max c inside the interval AB. Okay, now why do I say assume without loss of generality? Because it's possible that f has a min inside the interval AB. But if it has a min inside the interval AB, it's going to be the same argument. Okay, you can just apply the same idea. Okay, so I'm just going to say let's assume without loss of generality that f has a max at x equals c. And now what we're going to do is we're going to prove the derivative is 0 at that max. Okay, so what is the derivative f prime of c? So we know that f prime of c is going to equal to limit h goes to 0 of f of x plus h minus f of x divided by h. Now, this is the cool point, okay? So this is the cool point. Think about what that limit is, okay? This f of x plus h minus f of x by h is the slope of a secant line, okay? And as the secant line approaches, as h goes to 0, the secant line approaches a tangent line. Now, you kind of see that the slopes of the secant lines are going to be downward as we are going through points that are beyond x, so beyond c, okay? So greater than c, the slopes are downward. But if we take points that are less than c, so if we take h is negative, then the slopes of the secant line are going to be upward. Okay, you can kind of see that picture. What that means is that that's going to be the idea. We're going to take a left hand and right hand derivative and show that their signs are opposite somehow. And then we're going to conclude the only way that's possible is if the tangent line is horizontal or the derivative is 0. We're going to take the h goes to 0 from the right. H goes to 0 from the right of f of x plus h minus f of x by h. So as I showed you in the picture we just did, the secant lines go downward. If you have a max and your h is positive, your secant lines go downward. And so if your secant lines go downward, then what's going to happen? That's because it's a max. Okay, what does it mean to be a max? F of x plus h is less than or equal to f of x. So the numerator is always going to be negative because it's a max at it should not be x approaches 0, sorry, it should be c, sorry, it should be h approaches 0, but it should be c here. So we say f of c plus h, f of c, and we say f of c plus h, f of c. Okay, so I'm going to, I mean, everything I said is fine. We should just maybe call it c because I've said it as a max at x equals c. So what we can do now is we can say that that numerator is going to be less than or equal to 0. So this is going to be less than or equal to 0. Okay, because the numerator is always less than or equal to 0, the denominator is always at least 0. So whatever the limit is, every time, every h greater than 0, the expression is going to be less than or equal to 0. So the limit also has to be less than or equal to 0. It can't exceed 0, right? It cannot approach a positive number because it's always less than or equal to 0. Okay, so it cannot approach any positive number, so it's less than or equal to 0. Similarly, on the other hand, we know that the left-hand limit h goes to 0 from the left, of f of c plus h, so I'm going to put that in red as well, f of c plus h minus f of c, right, divided by h. Here, because h is negative, again it's the same idea because it's a max, f of c plus h when h is negative, your secant line, if you think about a max, a peak of the graph, your secant line is going to be sloped upward, right? So f of c plus h minus f of c, if you kind of have h is negative, then f of c plus h minus f of c is going to be negative. Okay, so again you're going to have a negative value because you're subtracting c plus h minus f of c, and then your denominator is going to be negative. So what you're going to get is you're going to cancel off the negative signs, you're going to get something non-negative, so that's why the secant line is upward. And so it's the same idea, numerator less than or equal to 0, denominator less than or equal to 0. So the limit is going to be of something that's always at least 0, and something that's always at least 0 cannot approach something that's negative. So the limit has to be at least 0. So here we're going to get this is at least 0. So that of course means because it's differentiable, the left-hand limit and right-hand limit are equal. So therefore, f prime of c is equal to 0, and that is the proof of Rolle's theorem. Okay, so that's a proof of Rolle's theorem. So I'm going to end the video here, but one more comment. Okay, one quick comment which I think is important is Rolle's theorem is false without all the hypotheses. So for example, we need that f has to be continuous on the interval, we need that it is differentiable on the open interval, continuous on the closed interval. Those are very important points. So for example, if you have a function, so I'll give you some cool counter examples that you can show your friends or your classmates. If you're studying this in university, it's a cool exercise to understand something. You want to understand, what if I remove the hypothesis, why does it fail? That's what's special about the result, is that the hypothesis makes it special. So if I have some graph like the following, where f of a is equal to f of b, but it is not differentiable, okay, something like a triangle, then Rolle's theorem fails because it's not differentiable, its derivative at that point is not 0, right? If you think of the derivative as the slope of the tangent line, if you take a left-hand limit of the derivative, it's going to be some kind of big positive number, and the right-hand definition of the derivative is going to be some big negative number. Okay, so in the proof, what would fail is that we are not using the fact that the left-hand and right-hand derivatives are equal, right? We use that because we knew f is differentiable, so then we could say less than or equal to 0, at least 0 means it's exactly 0. But if it's not differentiable, we can't use that. So we can't say the max has a derivative equal to 0. This is crucial because a quick tip for you, if you're studying calculus, like for example in college or high school, any context, when you're doing applied optimization problems in general, you want to consider critical points where the derivative is 0, they are going to be max and min, but also where the function is not differentiable. Like here, they could also be max and min. Okay, so that's an important example to keep in mind. And the other point is continuity. Well, continuity is a little bit more straightforward. Differentiability on the open interval implies continuity on the open interval, but even if you're continuous on the open interval, that's not enough, because if you have some function like this, this is an example, just a quick example, something like this, it satisfies that f of a is f of b, it's differentiable on the open interval ab, but it's not continuous, and so therefore, there's no Rolle's theorem fails. Okay, so we don't have a max or min inside the interval where we can say the derivative is 0. So thank you so much for watching. I hope you loved that video proving Rolle's theorem. The mean value theorem, which is probably the most important theorem in differential calculus, that is a corollary of Rolle's theorem. I'll do another video on that. But if you understand this, you can prove the mean value theorem using Rolle's theorem. It's a pretty quick proof. Okay, so thank you so much for watching. Every time I do these videos, I always ask for subscriptions, for liking, for sharing. The reason is I'm trying to create universal, infinite, free, accessible math education. My vision is to help as many people as possible and to change lives through math. To empower people to elevate themselves to higher levels in their life through math education. The beautiful thing about YouTube is it's all free. You're watching this all for free. There's no money. It doesn't cost anything. Liking and subscribing also doesn't cost anything. But what it does, it helps disseminate my videos to even more people who can then benefit from math. And ultimately, I'm really confident that through such free, accessible math education, we can change lives. And that's why I'm asking you to subscribe and like. And watching my videos, even if you've watched this far, that means a lot. I'm so grateful to you for your support. And I'm super excited to see you in the next video. I wish you all the best. I hope this video is able to support you. And I wish you all the best, wherever you are in the world, whatever time it is. I'm wishing you all the best to succeed with math, succeed in life. And I'm super excited to see you in the next video. So please take care.